Okay, let's begin. So, yesterday we defined the set FL of formulas for a predicate language L, and there are 4 different clauses. Oh, actually I forgot something. So, if R is an M-array predicate symbol, then and T1, T2, Tm are terms in context x bar, yeah, I mean x1, x2, xm are, xk are appropriate variables for those terms, then R of T1, T2, Tm, that is a formula. Yeah, formula is something which can be either true or false depending on the assignment. So, F1 prime, so we treat the only binary relation symbol in the meta language, namely equality symbol, specially, so that is F1 prime. So, T1, T2 are terms, then T1 equal to T2 is a formula. Yeah, I mean ideally it should be considered over here, but equality is always interpreted as the diagonal relation. So, that is why we do not want to mix these two things up. Third, so F2 is the clause which says that if phi of x bar is a formula, then so is negation phi, and if phi and psi are formulas, then so is their conjunction. So, this is something that you already know. Then F3 is the new clause, and that is what the first order logic is all about. It is quantifiers. So, this is, we are only talking about there exist. Okay. So, if phi is a formula and phi wj slash xi is the expression, see, by expression I do not mean formula. You simply take all the occurrences of xi and replace them with wj, then whatever expression you obtain, you put there exists wj at the front, and then that becomes a formula. Why we are doing this? Because we always want to use the letter w for quantified variables or bound variables. Yeah, that is why we are doing this. And the most important clause is nothing else is a formula. Everything should be determined by just these 4 clauses. Okay, so some bit of terminology here. Yeah, the formulas in FL which are only constructed using F1 and F1 prime, they are called atomic formulas. Why would they be called atomic formulas? Because they are not generated by using smaller subformulas. Yeah, they are unbreakable. If you think about negation phi, yeah, negation phi is actually obtained from phi. Phi conjunction psi is obtained from phi and psi. So, there are subformulas of those expressions, whereas once you consider these two, there are no subformulas. So, that is why they are known as atomic formulas. And an appropriate name for formulas constructed using only F1, F1 prime and F2, that is quantifier free formulas, right. So, that is another thing. Now, one thing that we have to talk about is the set of variables or the contexts. Yeah. So, I am going to use blue color to denote that. Yeah, I mean this is the set of free variables. Okay. So, if T1, T2, Tm are terms in context x bar, then what are the free variables in R, T1, T2, Tm? Free is something that is not bound by a quantifier. So, there is no quantifier here. Terms do not contain any quantifiers, right. Then So let me write this. So the set of free variables in R T1 T2 up to Tm is equal to the set of variables in one of the terms. You understand this? Suppose my term T1 is x and T2 is y, R is less equal. Then what is the set of free variables? X comma y. Right? I am taking union over here. You can see the set of variables in, let me call it variable, then maybe I will also call free variable f var, and set of variables in the terms Ti, you take unions. Yeah, simple thing. We are keeping track of the free variables over here. Okay, what is the set of free variables in T1 equal to T2? Any guess? The set of variables in T1 union set of variables in T2. Nothing different. Then the set of free variables in negation phi x bar is equal to the set of free variables in phi. We are not going to change anything. Then for conjunction, I am going to write it over here, free variables in phi conjunction psi, that is the set of free variables in phi union set of free variables in psi. So free variables are the variables which actually occur in those formulas. Okay? And finally, now this is the most important thing. So far we are only taking union, so it's boring. We have to cut down the number of free variables at some point, and this is the place where we do it. So the set of free variables in there exists Wj, phi Wj replacing xi is the set of free variables in phi and remove from there xi. So xi, if it occurs, then we remove it. If it doesn't occur, then we keep it as it is. But set subtraction is that. Yeah, a minus b is the collection of all those elements in A which do not occur in B. Right? So therefore, what we are doing here is we are simply removing xi from the set of free variables of phi, because xi was replaced by wj, and wj is attached to a quantifier. So therefore, it became a quantified variable or a bound variable. So therefore, it is no longer a free variable. You understand this? Let us do some exercises. Without that, you won't understand what I am saying. So give me some simple example of an atomic formula. Let me say in L set. Give me an atomic formula in L set.
X equal to y.
Right, x equal to y. This is an atomic formula. What else can you say in L set?
Or negation of x.
No, that is not an atomic formula. Negation is not an atomic formula. So x equal to y is the most general form, or x equal to x, or x equal to x are atomic. Give me some quantifier free things. Right, negation of x equal to y, conjunction z equal to y. Now this is a quantifier free formula. And at this point I will also ask you what is the set of free variables in here. So free variables in each case, x equal to y, what is the set of free variables? Huh? Just x? X comma y. What about this? Just x. What about this? Okay, whatever I am writing in blue letters, that will always be the set of free variables. Now tell me something more complicated, a quantifier included formula. What about our, okay, for all x there exists a y such that negation x equal to, oh sorry, I shouldn't do this. Suppose I start with x equal to y, yeah, then I'm just going to show you some transformation. I'm going to replace y by w1. Then what expression will I obtain? X equal to? So this is a formula. Right, this is not a formula, but I can write there exist after this. So now I am just going to apply this and going to say there exists a w1 such that x is equal to w1. This one is a formula. Okay. Now tell me what is the set of free variables in x equal to y? What is the set of free variables in this expression now? X. Yeah, we removed y. Okay, now again I am going to say that replace x by w1. Then what will I obtain? There exists w1 such that w2 equal to w1. This is not a formula. And finally I apply there exists w2. So what will I obtain? There exists w2, there exists w1 such that w2 is equal to w1. This makes sense? What is the set of free variables for this last formula? Empty. Okay. Now here comes an important definition. Say that phi of x bar in FL is a sentence if the set of free variables of phi is empty. Denote the set of all sentences, set of all L sentences by SL. Have you seen this notation before? SL, where? Propositional logic. So they are all sentences. They are formulas, but in particular they are sentences. Propositional formulas do not use any variables xi, do they? Propositional variables are nothing but zero-array relation symbols. So zero-array relation symbols that do not use any free variables at all. So therefore they do not use any quantifiers. The set of free variables in them is empty. So that's why we use the same symbol there, SL. Any questions about this? Okay, maybe we should formally write down, yeah, for all Wj phi phi Wj replacing xi is a short form for negation there exists Wj, negation phi Wj xi. Think about it, okay? When we say something exists, there exists a Wj satisfying certain property. At that time we are saying it is not the case that, if we say that for all Wj some property holds, so we are saying that it is not the case that there exists a witness where phi does not hold. Understand? That's why for all is negation, there exists negation. Okay? Hopefully everybody got this. Yeah? Huh? Yes, I am saying for all Wj phi holds. What is the meaning? That it is not the case that there is a witness as in there exists a Wj for which phi does not hold. Right? So that's why we are writing for all as a replacement for negation, there exists negation. But please do not write negation, there exists negation. After there exists, there should be a bound variable. Yeah? Okay. Now, suppose my formula is, let us go to some other example. Let us say orders. Now, can you tell me the definition that there is no upper bound, there is no maximal element? How can you say that? There is no maximal element in a poset. There exists a chain. What is a maximal element?
For every x greater than or equals to y, x not is equals to y doesn't hold.
For every x greater than equal to y,
X is equals to y doesn't.
x is equal to y doesn't hold.
For all x.
Yeah, if I write this thing down, yeah, I mean we are supposed to use bound variables. Now first of all tell me that there is no maximal element. What do you think, which kind of formula will it be? Will it be atomic? Will it be quantifier free? So it will be quantified. And what will be the set of free variables? There should be none. Yeah, it should be a sentence. We are talking about a property, right? If you talk about this property, then it is like directly either true or false in a given poset. Correct? So, something which doesn't depend on assignment of variables, that is a sentence. It's either true or false. Okay? So, this is the sentence which says that for all W1 there exists a W2 such that R W1 W2. Now this one expresses that. Can you see that? I mean, what should be R here? Less than. less than. Yeah, for all W1 there exists a W2 such that R W1 W2 that is less than. Yeah. So this is a sentence. Yeah, when R is interpreted as a strict partial order, then it says there is no maximal element. For every element there is a strict upper bound. That is what it means to say that there is no maximal element. But if I interpret on the other hand R as an equivalence relation, then this statement is still true. If R is an equivalence relation, then this is still true, right? What does it say? For all W1 there exists a W2 such that R W1 W2. What W2 can you choose for a given W1? W1 itself, right? So you can see, if R is interpreted as an equivalence relation, then this sentence is true. I'm just going to give you some hints, yeah, to understand. I mean, it's the same sentence, but it means something different if you interpret R differently. It says there is no maximal element in one case. In the other case, it says, it is always true. What do we need? We only need that the relation is reflexive. As soon as it is reflexive, this sentence is always true. Even though we haven't said what is truth of a formula yet, I think all of you can understand that this sentence is true in a reflexive, when R is interpreted as a reflexive relation. So formulas themselves do not mean anything. That's the purpose of writing this. Yeah, they are just formulas. Okay. So this is a sentence and you can write down the construction of this sentence like this. What do you start with? Rxy. Then you replace one of the variables by W2, the second variable. Then you put a quantifier and after that again you replace the other variable by W1 and then you put a quantifier. Right? So you understand how it is constructed. Okay, good. So let us do something more complicated. So in L ring, yeah, I think we should do the example that we talked about. So maybe I should remind you what L ring is. Right now I'm just going to use this notation F, G, H, C and E. Okay. Can you tell me what is F? Plus. So it is binary. G is multiplication, it is binary. H is subtraction, so that is unary. C and E are constant symbols, so that's zeroary. Okay. Now let us write down this. So is X a term? Yes? Is Y a term? Then is G of X, maybe I should say G of XX is a term? Similarly, g of y is a term, and then f of that is also a term. Then h of c is a term, and f of that is also a term, and this is a term, and 0 and e is a term, and equal to is a formula. Okay. What does it represent? Right. Not circle. It is simply the equation for circle. It doesn't mean circle. Circle is when you interpret this formula. Right now it just describes the polynomial equation for circle. Yeah, I mean our normal language we would write x square plus y square minus 1 is equal to 0. This is the equation for circle. Okay, so everything can be constructed as a formula, and see, now we can ask whether it is true or false. Is this expression true or false? Well, depends on values of x and y, but if I had not written this part equal to 0, then we couldn't ask whether it is true or false. At that time we could only evaluate it. Right. Okay, now what if I say start with this formula? This is a quantifier free formula. Suppose I call this formula phi xyz. Xyz is a context suitable for this formula. Yes, because the set of free variables is contained, yeah, in this. Maybe I should write that. Yeah, please write it. So say that x bar is a context suitable for a formula phi if the set of free variables in phi is contained inside x bar. Naturally. We don't care about the bound variables, yeah? So x bar should never include wj's. Okay, let's go here. So now I am going to say replace by w1 the variable z. What do I obtain? Same thing. And then apply there exists a w1. So I will write there exists a w1 such that x square plus y square minus 1 is equal to 0. What is the set of free variables for this? X comma y. So z was not present, but we could still replace it with this. I mean, essentially these two formulas are the same. But are they same or similar? They are not exactly the same. As formal expressions they are different, but they are similar. So eventually what will we show? They are logically equivalent. Correct? If that particular variable doesn't occur and then we are replacing it with a bound variable, then what's the problem? Yeah, I mean, the only thing is that here I cannot write z, I can only write phi xy. But this phi xyz and that phi xy, they are equivalent, not necessarily equal. I haven't yet defined logical equivalence, but I am showing you that you can bound any variable which may or may not occur in that formula. We have to allow this. Yeah, just for formality we have to allow these things. Okay, good. Now perhaps can you tell me in an appropriate language a sentence which says that in natural numbers, after every even number there is an odd number? When I say after every even number, what am I referring to? Plus 1 or less equal? Less equal. So I need less equal in my language. Okay. Then what else do I need? I want to express that something is odd or something is even. How do I express that?
There exists some natural number.
There exists a natural number such that
X can represent as 2 into 10 plus 1 or 0.
2 into something. Is 2 part of any language? So let's fix the language. Okay. So this is an example. Now here I am trying to explain to you how you can write down ordinary mathematical statements as formulas. So we want to express for each odd natural number there is an even natural number greater than it. Okay, so we have to do lot of things. But perhaps we can break this statement down a bit. First of all, we need to understand what is even and what is odd. For even and odd, he was talking about multiplication by 2. But what is really multiplication by 2? F of y. Yes, so basically, yeah, you are on the correct track. You are only using addition to describe multiplication. Right? Some number is even if it can be obtained by adding one number to itself. Right? That's even. So we have to express that. So we need something to say addition, to describe addition, right? And what else do we need in our language? We need less equal, greater than it, yeah? So we need less equal, and what else do we need? We need 1 in our language, right? Because we want to express odd. Odd is something times 2 plus 1. So we need 1. So what should we have? The structure that the least structure that we need is n, then we need plus, then we need 1, and then we need less equal. Okay, what is the language for this structure? Language is obtained by always hiding this part. So one binary function symbol, one constant symbol, and one binary relation symbol. So let me write down the language. It consists of f, which is 2, then e, which is 1, and then r, which is 2. Yeah, this is my language right now. Okay. Now let us break this particular statement down. It says that if a number is odd, then there is something which is greater than it such that the number is even. So perhaps if I have a formula which says that phi odd and it is true at a particular natural number, then there is a something such that W is even And what else?
W is greater than X.
W is greater than or equal to X. Now, so Rxw, and perhaps you should say something more, because R is interpreted as less equal. So what do we need to say? And X is not equal to. Yes, very good. So I should put a parenthesis around here and then say negation X equal to W. So what does this particular statement represent? So please pay attention to the brackets, yeah, how I am bracketing it. So it says that if X is odd, then there exists a W which is even and which is bigger than it. But the statement asks for each odd natural number, for each. So we should replace X by another bound variable. So maybe I should use W2. Yeah, so for all W2, now I will put a parenthesis. If phi odd W2, then there exists a W such that it is even and W2W negation W2 equal to W, then one bracket close and then this bracket closed. Okay, so this should represent what it is. Now tell me what is phi even. So what is phi even Z? Let's use W3 now. Huh?
For which f of W3 comma W3 is equal to
Very good. F of W3 comma W3 is equal to Z. Yeah, easy enough. Now, as you can see, I have already used W and W2. I needed a new variable, and that's why we started with a countable set of variables. I needed a new symbol, so it was available for me. Okay, what is phi odd? There exists a W4 such that f of W4 W4 1, no, not 1. What is the symbol here? E, right, E, and this is equal to Z. If you interpret your F, E and R in a different way, yeah, this particular formula will express something totally different. So the meaning of formulas, like converting our natural statements, mathematical statements into formulas, is perhaps easy, but interpreting them depends on the choice of structures. Okay, so perhaps now you are ready to understand how to describe interpretation of formulas. Yes?
so there can be, sir, here that implication is also not there, no? So we have to write it in.
Oh, I mean implication is not there, but you already know how to write implication as a derived connective. Yeah, so negation, this or that, and that or is again using De Morgan's law. I have already taught you propositional logic. Yes, so you are capable of doing that. Okay, let's proceed now. So the truth, yeah, I mean this is truth. Truth of a formula in FL. Okay, I want to understand the truth, but I should be given the data. Yeah, I mean just now we saw that we need help of a structure to understand something. So, suppose f suppose phi x bar is a formula for L and M is an L structure. Given a tuple A bar of length A bar in M of length equal to x bar. So, suppose the context is x1, x2, xk, then I should be given a tuple a1, a2, ak. Yeah. Say that the formula phi x bar is true in M at A bar written, how is it written? M satisfies phi at A bar if, the following happens. So, this is where our double turnstile has been introduced. Yeah. So, how do you read it? Yeah, it's a complicated way of reading. Phi is true in M at A bar. And notice that I am using curly M because I want to talk about the structure and not just a set. Another thing that you should notice, before I complete the definition, another thing you should notice is I said A bar in M. Technically speaking, this is wrong. Yeah, what I should be writing is A bar in M to the power length of A bar. But in logic, this is a common practice to suppress that power. Yeah, when we say A bar is a tuple from M, then I simply mean A bar is a tuple, each of the elements of A bar is an element of M. Yeah, only in logic we do this, yeah, not otherwise. You cannot say that 5, 7 is a tuple in R. Yeah, it's a tuple in R square, but in logic we allow that. Okay. Now, the definition as usual should proceed using recursion. Okay. So, T1 for truth 1. Yeah. If phi x bar is R T1 x bar Tm x bar for some M array relation symbol R and terms T1, T2, Tm, then M satisfies phi at A bar if and if, this is definition, so that's why I am not using if and only if, I am just using if. The tuple now, okay, so T1 is a term, we know how to interpret T1 in M, how to evaluate it. It is a function and we are evaluating that function at A bar. Then T2 at A bar Tm at A bar. Now this is all of them, yeah, T1, T2, Tm, when you evaluate at A bar, you will get a single element in M. So far we have an M tuple of elements of M. And this M tuple should belong to the interpretation of the relation symbol R in M. So whenever we think about less equal, yeah, when do we say less equal xy is true in natural numbers at 5 comma 6. When do we say that? Less equal xy. So x is interpreted at 5 comma 6 as 5. Y is interpreted as 6. So 5 comma 6 belongs to the relation less equal. What is the relation less equal on natural numbers? It's the collection of all pairs where A is less equal B. So we are writing simply that. Yeah, it belongs to the relation. Okay, if phi x bar is T1 x bar equal to T2 x bar, then M satisfies phi at A bar if T1 M A bar is equal to T2 M A bar. Yeah, here the interpretation of the equality symbol is the diagonal relation. Yeah, these two elements have to be equal. Okay, sorry, this is not T1, T2. Yeah, this is T1 prime. Okay, T2. If phi x bar is negation psi x bar, then M satisfies phi at A bar if M does not satisfy psi at A bar. Yeah, I mean does not satisfy, I am writing with a line across the double turnstile symbol. If phi x bar is psi 1 conjunction psi 2 x bar, then M satisfies phi at A bar if, can you tell me? M satisfies phi psi 1 at A bar and M satisfies psi 2 at A bar. Okay, and T3. If phi x bar, now I am going to use a slightly different notation, so please pay attention. If phi x bar is, there exists a Wj of psi x bar Wj, where psi x bar y is a formula. Okay, what did I do? Psi x bar y is a formula, and this formula is obtained by replacing variable y by Wj and then putting a quantifier. Yeah, so this is more appropriate. I am not saying Wj replacing y. I am simply replacing Wj in place of y. Yeah, that's more appropriate. Okay, if then M satisfies phi at A bar if, now there exists as a quantifier will be interpreted as there exists in semantics. If there is some B in the universe such that M satisfies psi at A bar comma B. If the inside formula is true when we substitute some B for that W. Think about it, that this is precisely what we do. I should do one example, yeah, before we leave. Yeah, perhaps let us say the same example that we were trying to do here, n plus 1 less equal. Yeah, and I will only talk about phi even z. So n plus 1 less equal, yeah, this is my thing, and then satisfies phi even at five if, what is the definition of phi even? Let me go back. There exists a W3 such that f W3 equal to z. Yeah, I mean n plus 1 less equal satisfies. There exists a W3 such that f W3 equal to z at 5. Okay, there is an existential quantifier over here. So when will this happen? If and only if there is some b, let us use the letter b, in natural numbers such that what will happen? The remaining thing is true. So f W3, now I am going to say f b comma b is equal to now z interpreted in perhaps I should be a bit more careful. Sorry. I will write it more properly. I will use another notation. So x hasn't been used here. Okay. So I will use f x comma x is equal to z. This formula, when evaluated at phi comma b, is true. If and only if what will happen? Now we have to interpret this formula. Yeah, this is a formula of constructed using what? Which clause? F1 dash. It is equality of two terms. So it is F1 dash. If and only if I will continue writing there is some b in the universe such that n plus 1 less equal satisfies. Now how do we interpret this? Something equal to something, let me show you. T1 dash was if their interpretations are same. So the interpretation of f is plus, yeah, I am just going to say, and x is interpreted as, this is the location for z, this is the location for x, right. So if and only if, plus of b comma b, b and b are interpretations of x at phi comma b, and z is interpreted as 5. Right. Now we can say, but is it the case that there is some b such that b plus b is equal to 5? No. So therefore, ultimately our claim is going to be it's not satisfied. Yeah, this is how you write things. And that's what we do. You can read formulas, you can understand whether they are true or false. Everything goes on here, but you have to learn how to write it on a piece of paper. It is interpretation of a formula in a structure at a tuple. Yeah, there are so many things and it takes time to get used to this language.